December 7th, 1943, Kriegsmarine Technical Testing Facility No. 4, Wilhelmshaven Naval Base. The cutting torch hissed as Korvettenkapitän Ernst Hoffmann's hand trembled slightly, preparing to open the sealed housing of the American fire control system. Around him, 8 of Germany's finest naval engineers leaned forward, their breath visible in the cold December air of the underground examination facility. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. For 3 years, Berlin had assured them that American naval technology remained inferior, mass-produced equipment created by a nation more concerned with quantity than quality. The Kriegsmarine Intelligence Service had reported that American destroyers relied on outdated fire control methods, primitive optical rangefinders, and manually calculated firing solutions that German crews could easily outmatch with superior training and Zeiss optics. Yet something was profoundly wrong. American destroyer escorts, ships built by the hundreds in shipyards that had never constructed warships before, were sinking U-boats with impossible accuracy. Their guns found targets in darkness and fog. Their depth charge patterns landed precisely where submarines desperately maneuvered. Their convoys maintained perfect formation through Atlantic storms that should have scattered them across hundreds of square kilometers. The equipment before Hoffmann had been salvaged 3 weeks earlier from a damaged American destroyer escort that had run aground during a confused night action off the Norwegian coast. The vessel, later identified through hull markings as a Buckley-class destroyer escort, had been attempting to intercept a German convoy when navigational errors and heavy seas drove it onto rocks near Statlandet. The crew had abandoned ship before German patrol boats arrived, but they had failed to completely destroy the vessel's most secret equipment. German salvage teams, working against tide and weather, had removed the ship's fire control radar system, its sonar equipment, portions of its radio suite, and most significantly, the mechanical computer that integrated all these systems into a unified fire control solution. These components, crated and transported under armed guard to Wilhelmshaven, represented the most complete capture of American naval fire control technology Germany had achieved. What Hoffmann and his team would discover over the next 72 hours would shatter every assumption German naval planners held about American industrial capacity, technological sophistication, and the fundamental nature of modern naval warfare. The mathematics of fire control were about to reveal a truth more devastating than any torpedo hit. Germany was fighting a 20th century war with 19th century methods, while America had industrialized naval gunnery itself. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The salvage operation had begun on November 14, 1943. Captain Lieutenant Friedrich Weber, commanding the patrol boat V-1506, had been conducting routine coastal surveillance when his radar operator reported a stationary contact near the Statlandet Peninsula. Approaching cautiously through heavy fog, Weber's crew discovered the American destroyer escort hard aground, listing 15 degrees to starboard, waves breaking over its stern. The vessel appeared abandoned. No lights showed, no response came to signal lamp challenges. No defensive fire greeted the approaching German patrol boat. Weber circled the wreck carefully, his crew at battle stations, expecting a trap. American destroyer escorts had proven themselves aggressive and capable opponents. Their willingness to charge U-boats on the surface, trading torpedo fire at point-blank range, had earned them respect and fear among Kriegsmarine crews. But this ship was genuinely helpless, driven onto rocks by weather and navigation errors during what German intelligence would later piece together as an attempted interception of coastal convoy HK-12. The American crew, following standard procedure, had attempted to destroy sensitive equipment before abandoning ship. Explosive charges had damaged the radar antenna, scuttling charges had opened seacocks, flooding the engine rooms, and thermite grenades had been used on coding machines and radio equipment. However, the 15-degree list and rapidly rising water had forced the crew to abandon ship before completing destruction procedures. The fire control equipment, located high in the superstructure and protected by armoured housings, remained largely intact. The mechanical computer, housed below the waterline but protected by watertight compartments, survived undamaged. Weber immediately radioed for salvage support. Within hours, teams from Wilhelmshaven arrived with cutting equipment, portable generators, and the specialized tools needed to extract intact equipment from a wrecked vessel. They worked through the night and following day, racing against weather that threatened to break the destroyer escort apart. By November 16th, they had removed the key components and transported them to Wilhelmshaven for examination. Korvettenkapitän Ernst Hoffmann received the assignment to lead the examination team on November 20th. At 41 years old, Hoffmann was one of Germany's most experienced naval gunnery officers. He had served aboard the cruiser Admiral Hipper during the Norway campaign, survived the battleship Bismarck's final action as a liaison officer studying British fire control techniques, and spent the last 18 months at the Naval Testing Facility analysing captured Allied equipment. His team included specialists in radar technology, fire control systems, mechanical computing, electrical engineering, and naval architecture. They were Germany's best technical minds, men who had designed the Kriegsmarine's own fire control systems and understood the theoretical limits of what was possible with available technology. The examination began on December 7, 1943, exactly 2 years after America's entry into the war. The coincidence was not lost on Hoffmann as he prepared his preliminary report. America had been in the war for 24 months. In that time, they had built an entirely new class of warship, the destroyer escort, and produced them in quantities that suggested industrial capacity beyond anything Germany could match. Intelligence estimates indicated that American shipyards had already launched over 200 destroyer escorts, with more building every week. These were not hastily assembled coastal patrol boats. They were ocean-going warships, displacing 1,400 tons, capable of 24 knots, armed with 3-inch guns, torpedo tubes, depth charge racks, and Hedgehog anti-submarine mortars. More disturbing still, every single one carried radar-directed fire control systems that integrated detection, tracking, and weapons delivery into automated solutions. The destroyer escort represented American naval philosophy made manifest. Equip them with sophisticated electronics that allowed minimally trained crews to fight effectively and rely on industrial capacity to replace losses faster than the enemy could inflict them. The equipment arrived at the testing facility in 12 wooden crates, each stenciled with German markings indicating contents and salvage date. Hoffmann's team began with external examination and documentation. Photographs were taken from multiple angles. Dimensions were recorded. Weight was estimated for each component. Serial numbers and manufacturer markings were carefully noted. The radar antenna assembly, despite damage from American demolition charges, revealed sophisticated engineering. The parabolic reflector, approximately 1 meter in diameter, was mounted on a rotating pedestal with elevation and training mechanisms. The construction was all welded aluminum, light but rigid, with waveguide feeds that suggested microwave frequencies rather than the longer wavelengths German naval radars used. Oberingenieur Klaus Richter, the team's radar specialist, examined the antenna mount closely. "This rotates continuously," he observed, pointing to the electric drive motors and slip ring assemblies. "Not scanning back and forth like our systems, but spinning constantly at perhaps 15 to 20 rotations per minute. The returning signals must be processed electronically to determine target bearing as the antenna passes." Hoffmann nodded. German naval fire control radars like the Fumo 23 used oscillating antennas that scanned back and forth across a limited arc. This approach was simpler mechanically, but slower to update target information. A continuously rotating system would provide more frequent updates but required sophisticated electronics to process the signals and extract useful targeting data. "What frequency?" Hoffman asked. Richter examined the waveguide dimensions and antenna characteristics. Centimetric, perhaps 3000 MHz or higher, based on these waveguide dimensions. This operates in the same frequency range as the British H-2S radar we captured at Rotterdam. The implications were immediate and disturbing. German naval radars operated at much lower frequencies, typically between 300 and 600 MHz. These longer wavelengths were easier to generate with available vacuum tube technology, but provided less accuracy and resolution. Centimetric radar, operating at 10 times higher frequency with wavelengths measured in centimeters rather than meters, offered dramatically improved accuracy for fire control applications. But centimetric radar required cavity magnetrons, sophisticated microwave generators that Germany could not produce in militarily significant quantities. The examination of captured British H-2S radar equipment in February 1943 had revealed British mastery of magnetron technology. Now, barely 10 months later, the Americans were installing similar equipment in destroyer escorts being mass-produced by shipyards across the United States. The Fire Control Director housing, a cylindrical armored structure approximately 2 meters tall and 1 meter in diameter, contained the optical rangefinder and director telescope, along with electronic interfaces for the radar system. Hoffman's team carefully removed the access panels, revealing the interior packed with equipment. "Everything is modular," noted Lieutenant Hans Becker, examining the mounting arrangements. "Each subsystem is a separate unit that can be removed and replaced without disturbing adjacent equipment. Look here." The radar receiver plugs into this interface panel with connectors that allow removal in minutes, not hours of rewiring. German fire control systems used custom installations where equipment was permanently wired during ship construction. Modifications or repairs required skilled technicians to trace circuits and make individual connections. The American approach sacrificed some performance for enormous gains in manufacturing speed, maintenance, simplicity, and combat damage repair. Every connector was standardized. Every wire was color-coded and numbered according to systematic schemes. The accompanying technical manual, salvaged from the wreck in surprisingly good condition, contained wiring diagrams, troubleshooting procedures, and replacement instructions written for operators with minimal technical training. "They assume the crew knows nothing," Becker observed, reading through the manual. "Every procedure is numbered steps. Troubleshooting uses decision trees. If this, then check that. Replacement instructions specify exact connector locations and pin numbers. There is no assumption of technical understanding, just the ability to follow simple directions." Hoffman considered this carefully. German naval practice assumed that fire control crews consisted of highly trained specialists who understood the theoretical basis of their equipment. Operators were taught principles of optics, mechanics, and ballistics. They could diagnose problems, perform field repairs, and adapt equipment to unusual situations. The American philosophy accepted that frontline operators were not engineers. Rather than train every destroyer escort crew to expert level, the Americans had designed equipment that functioned effectively when operated by adequately trained sailors, following systematic procedures. This required more sophisticated equipment, but it solved the fundamental military problem of expanding naval forces rapidly without requiring years of specialized training. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. The radar transmitter receiver unit removed from below decks revealed even more sophisticated technology. The housing, approximately 60 centimeters square and 40 centimeters deep, contained multiple chassis mounted on rails for easy removal. Each chassis was a complete subsystem: modulator, magnetron transmitter, receiver, intermediate frequency amplifier, and signal processor. Richter carefully extracted the magnetron assembly. The tube, designated 2J42 according to its marking, was similar in concept to the British cavity magnetrons examined earlier but showed distinct American design characteristics. The construction was robust, designed for reliable operation under combat conditions rather than maximum laboratory performance. "This is production equipment," Richter said quietly. "Not a prototype, not a laboratory model. This magnetron was built in a factory alongside thousands of identical units. The tolerances are remarkable. The construction quality exceeds our best laboratory work, but every aspect suggests mass manufacturing." He pointed to the machining marks on the copper cavity block. These cavities were precision milled, probably on automated machines rather than hand-fitted. The tolerances are extraordinary. The frequency control must be extremely stable. Yet the unit shows no evidence of individual tuning or adjustment. It was built to specification and installed without requiring a specialist to optimize performance. German magnetron development, still in experimental stages, required skilled technicians to individually tune each unit. The cavities were hand-machined, the coupling loops were adjusted empirically, and the magnetic field was optimized through trial and error. Production of 10 units required weeks of laboratory work. The Americans were producing thousands monthly in factories employing semi-skilled workers. The power output specifications marked on the magnetron housing indicated 40 kilowatt peak power, similar to British systems. But the pulse repetition frequency, the rate at which the radar transmitted bursts of energy, was higher than German systems, providing more frequent target updates. The entire transmitter-receiver system was designed for rapid target acquisition and continuous tracking. "This radar can track multiple targets simultaneously," Richter explained after tracing the signal processing circuits. The rotating antenna provides returns from all targets within range during each rotation. The electronics sort these returns, maintain tracks on individual targets, and update their positions continuously. German radars must choose a single target and manually track it, while losing information about all other contacts. The implications for naval combat were profound. A German destroyer engaging multiple targets would need to select one target, track it manually with radar or optical rangefinders, compute a firing solution, and only then shift attention to other threats. An American destroyer escort could simultaneously track every target within radar range, maintain firing solutions on multiple threats, and engage them in order of priority without losing awareness of the tactical situation. But the most shocking discovery waited in the fire control computer, the mechanical brain that transformed raw sensor data into accurate firing solutions. The device, designated Mark 1A according to its nameplate, was housed in a watertight cylindrical case, approximately 1 meter tall and 60 centimeters in diameter. It weighed approximately 180 kilograms, far heavier than expected for its size. Hoffman and Becker carefully opened the case on December 9th, 2 days after beginning the examination. What they found inside defied their understanding of mechanical computing. The device contained hundreds of precision gears, cams, differentials, and integrators arranged in a three-dimensional assembly that packed extraordinary computational capability into a compact space. "This is not a simple ballistic calculator," Becker said slowly, tracing the mechanical linkages. "This is integrating multiple variables continuously. Look here, radar range and bearing data enters through these input shafts. Here, optical rangefinder data can be manually input. These gears compute target motion. These cams correct for parallax between the radar and guns. These integrators calculate continuous firing solutions as the ship and target maneuver." He pointed to a series of differential assemblies. "These are solving the fire control problem geometrically using mechanical computation. The target's position, course, and speed are mechanically represented. Our ship's position, course, and speed are mechanically represented. The computer continuously calculates the point in space where shell and target will meet, correcting for projectile ballistics, wind, ship motion, everything." German fire control computers existed, but they were simpler devices that required manual inputs and provided static solutions. An operator would input target bearing and range, estimate target course and speed, input own ship's motion, and the computer would output gun bearing and elevation. As either ship maneuvered, the operator would need to update inputs and recalculate. The process required skilled operators and provided solutions that rapidly became obsolete in dynamic combat situations. The Mark I, a computer operated continuously. Radar automatically fed current range and bearing data. Ship's gyro compass automatically provided own ship heading. Speed inputs came from propeller revolution counters. The computer output gun orders directly to the gun mounts without human intervention beyond target designation and firing authorization. They have automated fire control, Hoffman said quietly. From detection to gun laying, the entire process is automatic. The radar detects a target. The computer solves the fire control problem. The guns train and elevate automatically. The crew simply authorizes firing. German gunnery requires skilled operators making continuous judgments and adjustments. American gunnery requires someone to push a button. The examination continued for another week. Each subsystem revealed the same pattern. Sophisticated equipment designed for operation by minimally trained users, modular construction allowing rapid replacement, and integration into automated systems that removed human limitations from the fire control loop. The sonar equipment, designated QC sonar according to US Navy markings, used similar principles. Automatically rotating transducer, continuous echo ranging, integrated displays that showed target bearing and range without complex calculations. A sonar operator, with a few weeks of training, could effectively hunt submarines using equipment that did the complex signal processing automatically. The radio equipment followed the same philosophy: crystal-controlled transmitters and receivers with push-button frequency selection. Modular construction allowing field replacement of failed units. Integration with the ship's Combat Information Center, where all sensor data converged for tactical decision-making. Every system reflected the same American approach. Build sophisticated equipment in quantities sufficient to equip hundreds of ships. Design for operation by adequately trained personnel rather than specialists. Integrate everything into automated solutions that removed human error and variability from critical functions. Hoffman's preliminary report, submitted to Oberkommando der Marine on December 22, 1943, was 47 pages of technical analysis and strategic assessment. The conclusions were devastating. American destroyer escorts represent a revolution in naval warfare. They are not superior ships in traditional measures of speed, armor, or gun caliber. They are superior in their integration of detection, computation, and weapons delivery into automated systems that function effectively with minimal operator training. The fire control system examined integrates centimetric radar, mechanical computing, and automatic gun laying into a capability that exceeds our most advanced fire control by a factor of at least 5 in accuracy and 10 in reaction time, where German gunners must detect, range, track, compute, and lay manually through a series of skilled operations taking minutes. American systems perform the entire sequence automatically in seconds. More critically, this equipment is clearly production designed. Every aspect suggests manufacturing in quantities of hundreds or thousands. The Americans are installing these systems in every destroyer escort, possibly in every escort, vessel, and major warship. They are creating a fleet where every ship possesses fire control capabilities that Germany reserves for only our most modern capital ships. The report estimated that American shipyards were producing destroyer escorts at a rate of 4 to 5 per week. If each carried fire control systems of this sophistication, American naval capabilities were expanding faster than German forces could counter. The Battle of the Atlantic, already desperate following the May 1943 disaster when U-boat losses became unsustainable, was being lost not through tactical failures, but through American industrial and technological superiority that Germany simply could not match. Hoffman concluded his report with an assessment that would prove prophetic. The examination of this equipment reveals that America possesses not just superior industrial capacity, but a fundamentally different approach to warfare. They have industrialized combat itself, applying mass production and automation to fire control, detection, and weapons delivery. German naval forces rely on superior training and individual skill. American forces rely on superior equipment that makes training less critical. We cannot defeat this approach through better tactics or braver sailors. We can only match it through equivalent industrial capacity and technological sophistication. Germany possesses neither. The implications are inescapable. American naval superiority will increase continuously as more vessels enter service with these capabilities. Unless fundamental changes occur in German shipbuilding and electronics production, changes that would require years we do not have, American victory at sea is mathematically certain. The report was classified most secret and distributed to only the highest levels of Kriegsmarine Command. Grand Admiral Karl Dönitz, who had succeeded Erich Raeder as Commander-in-Chief of the Kriegsmarine in January 1943, read Hoffmann's assessment with grim understanding. Dönitz, more than any other German officer, understood what American destroyer escorts represented. His U-boat force had been the Kriegsmarine's most effective weapon, the only German naval capability that seriously threatened Allied operations. U-boats had sunk millions of tons of merchant shipping in 1942, bringing Britain close to starvation and threatening to delay or prevent American military buildup in Europe. But by late 1943, that campaign was failing. American destroyer escorts, purpose-built for anti-submarine warfare and produced in overwhelming numbers, were the primary reason. They were slow by destroyer standards, their 24-knot maximum speed barely faster than surfaced U-boats. They carried smaller guns, only 3-inch weapons compared to the 5-inch guns of fleet destroyers. They lacked the armor and torpedo batteries of true warships, but they were built for one purpose: hunting submarines. Their sonar could detect submerged U-boats at ranges up to 2,000 meters in good conditions. Their radar could spot surfaced U-boats from 20 kilometers or more. Their Hedgehog anti-submarine mortars threw patterns of contact-fused projectiles that killed with a single hit, unlike depth charges that could miss by meters and merely damage. Most critically, they existed in numbers that allowed constant convoy coverage. By late 1943, every Atlantic convoy sailed with destroyer escort protection. U-boats that had operated with relative impunity in 1942 now faced dedicated submarine hunters, equipped with detection and weapons systems, against which they had no effective counter. The captured fire control equipment explained why destroyer escort gunnery was so devastatingly effective. When U-boats attempted to fight on the surface, using their deck guns against approaching escorts, they faced enemies whose guns found them instantly despite darkness, weather, or evasive maneuvering. The automated fire control gave destroyer escorts enormous tactical advantages. Dönitz convened a crisis conference at his headquarters near Berlin in early January 1944. Attending were his senior staff officers, representatives from the Reich Ministry of Armaments, naval architecture experts, and the scientists responsible for German radar and fire control development. Hoffmann presented his findings from the captured equipment examination. The response was silence. The implications were too devastating to acknowledge immediately. Finally, Vice Admiral Eberhard Gott, Dönitz's chief of staff for U-boat operations, spoke. If the Americans can build this equipment and install it in ships being produced at 5 per week, then our U-boats face enemies we cannot defeat through existing tactics or weapons. Every destroyer escort possesses detection and fire control capabilities superior to our surface warships. They are being produced faster than we can sink them, and each one makes the Atlantic more dangerous for our boats. Someone asked whether Germany could develop equivalent systems. The answers from the technical experts were uniformly negative. German industry could theoretically design similar equipment, but production would require specialized factories, trained workers, and materials that were simply unavailable. The copper needed for waveguides, the precision gears for mechanical computers, the specialized vacuum tubes for radar receivers, all were in critically short supply. More fundamentally, Germany lacked the industrial infrastructure for mass-producing complex electronic and mechanical systems. German manufacturing excelled at producing sophisticated equipment in small quantities, crafted by skilled workers using traditional methods. American manufacturing excelled at producing adequate equipment in vast quantities, using semi-skilled workers, specialized machinery, and systematic production methods. One philosophy could equip dozens of ships, the other could equip thousands. The meeting reached the same conclusion Hoffman's report had stated. Germany could not match American naval technology through crash programs or industrial mobilization. The gap was too large, the time remaining too short, and the required resources too scarce. The only options were tactical adaptations and new weapons that might provide temporary advantages before American countermeasures neutralized them. But tactical adaptations could only slow defeat, not prevent it. The mathematics of industrial production were inexorable. The desperate search for countermeasures began immediately following the January conference. Kriegsmarine research facilities, already stretched thin, supporting U-boat development, aircraft radar warning systems, and acoustic torpedo programs, received new directives to develop technologies that might neutralize American destroyer escort advantages. The task was impossible. Germany was being asked to bridge in months a technological gap that had taken America years to create, using industrial resources that were a fraction of what American factories possessed, while Allied bombing systematically destroyed German production capacity. Nevertheless, German engineers attempted the impossible because duty demanded it. Telefunken began work on improved naval fire control radars operating at higher frequencies. Siemens developed prototype mechanical computers with capabilities approaching the captured American Mark IB. Specialized firms experimented with automated gun-laying systems that could integrate radar data directly. Every program encountered the same obstacles. Precision components required specialized machine tools that were being destroyed by bombing faster than they could be replaced. Skilled workers were being drafted into combat units or killed in air raids. Raw materials, particularly copper, aluminum, and specialized alloys, were diverted to aircraft production and other higher priority programs. Most critically, even if prototypes succeeded, Germany lacked manufacturing capacity to produce equipment in militarily significant quantities. A system that took 6 months to develop and could be produced at a rate of 10 units monthly was strategically worthless when the enemy fielded hundreds of equivalent systems. The acoustic torpedo program represented Germany's most successful attempt to counter destroyer escort advantages. The G7S torpedo, designated T5 Zongkönig or Wren, used passive acoustic homing to guide itself toward the propeller noise of enemy ships. Introduced in September 1943, the weapon achieved initial success against convoy escorts. The concept was sound. Destroyer escorts hunting U-boats made considerable noise with their high-speed propellers. A torpedo that could home on this noise would theoretically allow U-boats to sink escorts before they could drop depth charges or fire hedgehog mortars. Early reports showed several escort vessels damaged or sunk by acoustic torpedoes. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. But Allied countermeasures appeared within weeks. The Foxer noisemaker, a simple device towed behind ships creating louder propeller noise than the ship itself, successfully decoyed acoustic torpedoes. More sophisticated versions followed rapidly. By early 1944, acoustic torpedoes were sinking fewer escorts, while Foxer-equipped destroyer escorts continued hunting U-boats with undiminished effectiveness. The pattern repeated across every German countermeasure attempt. German scientists would develop a weapon or technology that provided temporary tactical advantage. Allied scientists would analyze captured examples or infer operating principles, then develop countermeasures. Allied industrial capacity would produce countermeasures in quantities sufficient to equip entire fleets. German advantages would evaporate before they could be fully exploited. The fundamental problem was not German technical incompetence. German scientists and engineers were among the world's finest, and their theoretical knowledge often exceeded Allied understanding. The problem was industrial capacity and production philosophy. German industry could not translate scientific knowledge into mass-produced weapons fast enough to affect the war's outcome. Korvettenkapitän Hoffmann continued examining captured American equipment throughout 1944. Each new example reinforced his original conclusions while adding disturbing details about American technological progress. In March 1944, salvage teams recovered sonar equipment from a destroyer escort damaged by a mine off the French coast. The sonar, a newer model than previously examined, showed incremental improvements in range, resolution, and reliability. They are continuously improving their equipment, Hoffmann noted in his March report. This sonar incorporates design changes that address problems we identified in earlier models. The Americans are learning from operational experience and incorporating lessons into ongoing production. German equipment, in contrast, often degrades in quality as the war progresses due to material substitutions and workforce changes. In May 1944, German forces captured intact radar equipment from a destroyer escort severely damaged during the Normandy invasion. The radar, designated SG Surface Search Radar, operated at 3,000 MHz with improved range and resolution compared to earlier systems. More significantly, it showed evidence of rapid production techniques that suggested American factories were building these units at rates of hundreds per month. Every component is standardized, Hoffmann's report noted. Vacuum tubes follow common base configurations, allowing interchangeability. Resistors and capacitors use color codes, indicating American industry has standardized component values across manufacturers. Even mounting hardware uses unified thread standards. This standardization means that American factories can shift production between different equipment types without extensive retooling. Components from one radar can repair others. The entire system is designed for industrial flexibility and production scale. German radar production, in comparison, used custom components for each equipment type. The Fumo 24 naval radar shared virtually no parts with the Fumo 25 despite similar functions. Changing production priorities required months of retooling. Component shortages in one system could not be addressed by cannibalizing parts from different systems because nothing was interchangeable. The captured equipment also revealed American progress in miniaturization and reliability. Newer models were smaller, lighter, and more robust than earlier versions. Mean time between failures was increasing while maintenance requirements decreased. The Americans were not just producing more equipment, they were producing better equipment at an accelerating rate. German technical intelligence compiled comprehensive assessments of American naval electronics production by mid-1944. The numbers were staggering. American factories were producing annually what would take Germany decades to manufacture. Destroyer escorts alone required thousands of radar sets, sonar systems, mechanical computers, and radio installations. American industry supplied all of it while simultaneously equipping hundreds of other vessels and supporting Army and Air Force electronics requirements. The source of this capacity became clear through examination of manufacturer markings on captured equipment. Companies like General Electric, Western Electric, Raytheon, and RCA operated factories employing tens of thousands of workers. These firms had transformed from civilian electronics manufacturers into military suppliers without losing their mass production expertise. Detroit automotive companies contributed mechanical computing expertise, adapting gear cutting and precision machining techniques from automobile transmissions to fire control computers. The Ford Instrument Company, originally a manufacturer of precision gauges, produced thousands of mechanical computers using assembly line techniques refined in automobile manufacturing. This industrial ecosystem simply did not exist in Germany. German electronics firms remained organized as they had been in the 1920s, small manufacturers producing specialized equipment using skilled craftsmen. Production quantities were measured in hundreds per year, not thousands per month. Quality was maintained through individual inspection and hand adjustment, not statistical process control and automated testing. The psychological impact on German naval personnel became evident through interrogation reports of captured crews and intercepted communications. Allied intelligence officers noted that German sailors, particularly those who had served in 1942 when U-boats dominated the Atlantic, showed profound demoralization when discussing American destroyer escorts. Kapitän-Leutnant Hans-Joachim Hesse, commanding U-boat U-415 when it was sunk by the destroyer escort USS Bostwick on July 14, 1944, provided detailed testimony during interrogation at Fort Meade, Maryland. The transcripts, declassified in the 1980s, reveal the crushing psychological effect of technological inferiority. We knew by mid-1943 that the Americans possessed detection equipment against which we had no effective countermeasures, Hesse told interrogators. Their destroyer escorts found us regardless of weather, darkness, or evasive maneuvers. They maintained contact even when we went deep and silent. Their depth charges fell with precision that suggested they knew our exact position and depth. The radar warning receivers we carried were supposed to alert us to approaching aircraft and surface vessels. Sometimes they worked, giving us minutes to dive. Often they gave no warning at all. We suspected the Americans had multiple radar frequencies, and our receivers could only detect some of them. Later we learned this was true. The Americans could choose which radar to use, selecting frequencies our receivers could not detect. Hesse described a patrol in May 1944 that exemplified the hopelessness of U-boat operations against well-equipped destroyer escorts. His boat had been stalking convoy HX 293 inches the North Atlantic, attempting to reach attack position against the merchant ships. 3 destroyer escorts screened the convoy: USS Thomas, USS Bostwick, and USS Bronstein. We detected the convoy at 40 kilometers range using our passive hydrophones, Hesse recalled. We maneuvered submerged to intercept, moving slowly to avoid detection. At 20 kilometers, one of the escorts suddenly increased speed and turned directly toward us. We had made no noise, transmitted no signals, shown no periscope, yet somehow they knew our position. The destroyer escort approached at high speed while we went deep and rigged for depth charging. The first pattern fell directly overhead, close enough to knock out our lights and crack gauge glasses. We altered course and increased depth to 200 meters. The escort followed us perfectly, dropping another pattern that caused serious damage to our stern torpedo tubes. We attempted every evasion tactic, stopping all machinery to become silent, releasing bold decoys that created false sonar targets, blowing oil and debris to simulate a kill. Nothing worked. The escort maintained perfect contact for 6 hours, calling 2 more destroyer escorts to assist. They took turns depth charging us, while their sonar tracked every movement we made. Finally, with the hull cracking from pressure, batteries exhausted, and air becoming toxic, we were forced to surface. The 3 escorts were waiting in perfect positions to fire. We were surrounded before we could fully blow ballast. The Americans took us prisoner, 47 men from my crew. 16 had been killed by depth charge damage. The boat sank within minutes of our evacuation. Hesse's interrogators asked what equipment the Americans had used to detect his submarine. He replied that he didn't know precisely, but post-war analysis suggested it was likely the QHB sonar system, an advanced echo-ranging equipment that could detect submarines at extended ranges and maintain contact even against sophisticated evasion tactics. The QHB represented another example of American technological superiority. The sonar used multiple transducers, sophisticated signal processing, and automatic tracking circuits that could follow maneuvering submarines while filtering out false returns from marine life, thermal layers, and bold decoys. German sonar technology, focused primarily on passive listening, could not match the active detection capabilities American systems achieved. Other captured U-boat commanders told similar stories. Kapitän-Leutnant Helmut Frömsdorf, whose boat U-984 was sunk by USS Buckley on March 16, 1944, described the engagement as a complete technological mismatch. The destroyer escort detected us at ranges where we could not even see the convoy, Frömsdorf stated during interrogation. When we attempted to attack on the surface at night, their radar found us instantly. When we submerged and tried to evade, their sonar tracked us perfectly. When we attempted to fire acoustic torpedoes at the escorts, their noise-making devices decoyed the weapons. They possessed answers to everything we attempted. The battle between U-984 and USS Buckley on March 16th had been particularly violent. Frömsdorf had attempted to press home a surface torpedo attack, gambling that his boat's speed and maneuverability could get him close enough to fire before being destroyed. USS Buckley's radar detected the surfaced U-boat at 12 kilometers range in complete darkness. The destroyer escort's fire control computer automatically calculated the U-boat's position, course, and speed from radar returns. Gun directors trained and elevated without human intervention beyond the order to commence firing. 3-inch shells began falling around U-984 within 30 seconds of initial detection, a response time impossible with manual fire control. Up next, you've got 2 more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.